Well, at last we've reached the final unit for the year, electrochemistry. Part of the reason why I deliberately choose to do this last is because it really ties in with both thermochemistry, delta G, and with equilibrium. And so this is also a good opportunity for us um, to tie those particular things back in. So, uh, so I will be including questions on those two areas. This is a very, very important area. It will come up in the free response section. It will be parts of questions or entire questions. You need to go back to chapter 4 from the first unit and review everything you know about oxidation reduction reactions. I have posted a POGIL worksheet on oxidation reduction, and these reactions always occur in pair. Wherever there is a reduction reaction, there is a oxidation reaction. Now, the last point here is about oxidizing and reducing agents. That is no longer part of the terminology that's used in APs. The idea was that a chemical that is itself reduced but causes others to be oxidized as an oxidizing agent, but they no longer use that particular terminology anymore. Right, so what we need to do is just revise how to assign oxidation numbers. So like in this example here, fluorine is assigned an oxidation number of -1, so sulfur will be +6. Oxygen is assigned an oxidation number of -2. There's got to be a minus overall, so nitrogen will be +5. So just revise that. Then also you need to revise the whole idea of how to balance a redox reaction. This hasn't come up very often in a free response question, but it has come up in multiple choice. So it is worth going back and just remembering the process. Half equations, then balance the oxygens using water, balance the hydrogens using H+, and then balance the charges, and then bring the two together. So, under this, we're going to talk about two types of cells, galvanic cells and electrolytic cells. So galvanic cells are ones where the chemical reaction results in electrical energy, more commonly known as batteries. There are two electrodes separated by a wire which allows the electrons to transfer, and there is always a salt bridge which allows the ions to move back the other way. So here is an example of two models. You have the two different beakers with a salt bridge in the middle, or you have two different beakers with a porous disc in the middle. The point is that there has to be a complete circuit. If you take the salt bridge out, the reaction stops, because as soon as the salt bridge comes out, ions build up in each of the beakers, and so therefore the reaction cannot proceed. Cell potentials are when you actually put it's how much, what is the electromotive force? How much pushing power does it have, or voltage? I think one of the best analogies that I use in class to describe the difference between voltage and amperage is to think about a waterfall. If you think about a waterfall, the height of the waterfall is the potential difference, which is the voltage. It doesn't matter how much water flows across that waterfall, it will still have a certain amount of potential energy that's released. So it may be just a trickle, it may be a Niagara Falls, but the point is that the height is the voltage, the electromagnetic motive force. The amount of water going over corresponds to the number of electrons that are flowing through the wire, and that represents the current, okay, the amperage. So the electrical potential unit is 1 joule of work per coulomb of charge. Coulombs are then used to work out in terms of chemistry. We can go from coulombs to moles, and so that's the unit that we use. It's the units used in physics if you've done electrical work, but in chemistry we think in terms of electrons. So here, for example, is a copper zinc cell. So you have copper in one and zinc in the other. You separate the two cells, and then what will happen is the potential difference is the difference between the zinc's pushing electrons towards the copper and the copper absorbing those electrons, and it is 1.1 volts. Okay, obviously in the first cell on the left there is some slight resistance, so therefore it is slightly lower. Here is another example of a standard reduction, but this shows the standard reduction potential, which is the hydrogen electrode. Now the hydrogen electrode is hydrogen gas at 1 atmosphere pressure, hydrogen ions at 1 molar, standard temperature, which for electrochemical cells is 25 degrees Celsius. So what happens is the hydrogen electrode is taken as the standard reduction potential and is nominally given a value of 0. Then everything else is compared to that and given their own values. So what it means is that as a result you can produce a table of standard electrode potentials and then compare them. Now there have been questions come up in the past where they have just chosen another random chemical as the standard potential, but the point is that it's the relative charge of the two things that then you can then calculate out the potential. So at a microscopic level for this reaction, what's happening is zinc metal is turning into zinc ions. The electrons are then passing into the wire. They're then coming down into the copper, where the copper ions are turning into copper metal. Now, the point and the potential difference between the zinc's ability to push electrons and the copper's ability to absorb electrons is 1.1 volts. You have been asked in the past in AP questions to represent this, to actually show the direction of electrons and the direction of ions, etc. Calculating cell potentials, you take the list of standard cell potentials, which standard, as I just said, was 25 degrees Celsius, 1 molar, and 1 atmosphere pressure. And they are always listed as reduction potentials. So one of them is going to need to be reversed to get an oxidation, because there's always an oxidation and a reduction. The little mnemonic that I find useful is this idea of RegCat and ANOx. You could also think of it in terms of the constants and the valves. So what happens is reduction occurs at the cathode and oxidation occurs at the anode. So in an E cell potential, you take the cathode reaction and take the voltage as it is listed, and you reverse the voltage for the anode reaction because it is listed as a reduction potential and you need it to be listed as a oxidation potential. Here is an example of standard potentials. You do not need to memorize anything like this. What will happen is that you will be given these in any question that you're given in APs. It used to be that you were actually given the table of all of them. Nowadays they just give you the ones that you need. Other things that you may have seen in the past, you may have seen something like a reactivity series, which is identical to this except without the voltages. Notice they're all listed as ions plus electrons leading to an atom or another type of ion. So and if you look, you can see the potential for that's 0 is the hydrogen potential. So the ones below it are the ones that are more reactive than hydrogens, the ones about less in terms of gaining electrons. Right, the line notation is rather than drawing it all the time, we can draw a simple line notation. And this is a slide we're stopping on and studying. The single line denotes a phase boundary, so in this case between magnesium and magnesium ions and aluminium ions and aluminium. It's always written in the order in which the reaction occurs. So magnesium is turning to magnesium ions and aluminium is turning into aluminium metal. The double line represents the salt bridge. Okay, so we can work out cell potentials in terms of the overall relationship between the work done and the energy involved. Now, where the E of the potential difference is the charge in coulombs transferred. So 1 amp is 1 coulomb per second of electrons passing a point. Remember that 1 volt is 1 joule per coulomb. Now, the charge on 1 mole of electrons is a constant called Faraday's, so which is the value of 96,485, and this number is given to you in the data sheets. So it's that many coulombs, 96,500 approximately, coulombs of charge per mole of electrons. Okay, that's the relationship with moles and Faraday's. So for standard conditions, delta G equals the number of moles of electrons times the Faraday's constant times the standard potential. And notice this is a negative number because if the reaction is occurring spontaneously, it will be the E0 will be positive. Another thing which is less asked about now is the relationship of concentration cells. So what happens if you have two identical chemicals, but in this case one side is at 0.1 molar and one side is at 1 molar? The electrons will move in such a way so that the two cells end up with the same concentration. And this involves the Nernst equation, which is nowadays not asked for in APs. But some awareness of it is worthwhile knowing, and you do need to realize that there is a direct relationship between equilibrium constant and the cell potential. So the last equation is the one that's more likely to be asked about, where they've been turned into the actual for natural log, not natural log, log to base 10. There is some examples of two very common types of batteries, the lead storage battery you find in cars and the common dry cell. You've got mercury cells, which you've all come across, and fuel cells, which are becoming increasingly important. Corrosion. Make sure that when you talk about rusting only refers to the corrosion of iron. It does not refer to other corrosions. Okay, so do be quite specific about that, and it is sped up by the presence of water. You can prevent corrosion through galvanizing, painting, alloying, and cathode protection. These are occasionally asked about. Electrolysis. This is a process where we drive the reaction backwards by adding electricity. In this case, this is electrolysis of water, and you can see that there's twice as much hydrogen as oxygen being produced. We did an electrolytic process with the copper. Here, aluminium, the production of aluminium is an important part of example, as is metal plating. The down cell to produce chlorine gas, and the mercury cell to produce sodium hydroxide are also other important industrial processes. So that concludes that particular PowerPoint. So I do go through the PowerPoint, study it in detail, and have a good week. I have set quite a lot of work for you to work on, mostly POGIL exercises, and I will download some AP questions. There are AP questions every year, so if you want to have a look at them, just go into any year at random and have a look at the AP questions. Okay, have a good day.